So you can see my screen, right? Hello? Okay. Okay, so it's already 10 and let's get started. Okay, I think more are joining right now. So, but we'll just get started. Okay, so this class we're going to start on the single particle dynamics. Okay, so before you introduce the new contents, again, we'll do a quick recap. Okay, so last class we mainly talk about one example to calculate the particle removal efficiency. And we said that we should use these two equations for the removal efficiency. So for these two, this one is for the mass removal efficiency, right? And this one is for number removal efficiency. So basically, it's in the denominator, we have the total mass or the total number, and then the numerator, we have the mass of the particle that's being removed, right? And to calculate that, we need to do the summation of particle removal efficiency multiplied by the mass in that size range. And we give an example of how we can use the log normal distribution, the semi-log plot, to find out what is the mass fraction in each size range. And in that way, we can do this summation and then calculate what is the total collected mass. Okay, so it's going to be the same for the total number removal as well, right? So last class, we also talked about the team project. I hope you guys can reach out to your teammates earlier rather than later, okay? Because it's going to take quite a lot of efforts to accomplish this project, okay? And now let's talk about the particle dynamics. So whenever we talk about dynamics, right, the dynamics of a particle or the dynamic of a system, we want to know what is the force, okay? So basically it's the movement of the particle. And we know that if a particle move around, right, there must be some force, okay, that's pushing this particle to move, okay? So in order to know what is the dynamics of particle, we have to know what are the typical forces on a particle. Okay, so I can give a few examples, right? So for example, let's say that I got a flu, all right? So it happens that I was sneezing and then I emit a droplet that's coming out of my mouth, okay? So what are going to be the probable forces that can act onto this particle? So maybe I can give a quite uncommon force. I would say that buoyancy is a force, okay? For example, buoyancy. So we know that the buoyancy is calculated by rho F V multiplied by G, right? Where the F is the fluid density or the air density, right? V is the volume and G is the gravity, okay? That is buoyancy. So what is a common force? So common force is gravity, right? As you can imagine, the droplet is going to fall onto the ground. So we have the gravity, and the gravity is calculated by Fg, which is equal to mg, okay? So the mass multiplied by gravity. And further, you have rho particle multiplied by V multiplied by G. Okay, so notice the difference here. So the gravity is using the density of the particle, while the buoyancy is using the density of the fluid, okay? And further, if we assume that the particle volume or the particle is a sphere, right? That's what we said in the beginning. So the volume is going to be equal to pi over 6 dp to the third, right? And we can just plug in this volume to get what is the force acting onto the particle. All right, so this is gravity and buoyancy. What are the other common forces? Let's say that, well, I emit this droplet into the air. I also have some charging device. Let's say that I'm on charge, okay? I accidentally plug my finger into the power stripe, okay? That I give these particles some positive charges. And then if these particles went into an electric field, then there's going to be an electrostatic force, okay? So that's going to be static, right? Fe is equal to Q multiplied by E. where Q is basically the charges or the charge on the particle, and E is the electric field strength. Okay, so this is how we can calculate the electrostatic force. And further, we know that the charge on the particle, it has to be an integer number of either electrons or positive charges, right? So Q is further equal to N multiplied by E. Okay, so this N here can be positive or negative. Let's say it has to be an integer. It has to be 0, 1, 2, so on and so forth, or it can be minus 0, minus 1, minus 1, minus 2, and so on and so forth. Okay, it has to be an integer number. And the E here is an elementary charge. That's 1.6 multiplied by 10 to the negative 19 Coulomb. Okay, so this is the charge that's carried by one single electron. Okay, so this is electrostatic force. So what are the other forces or possible forces? Okay, so one possible force is what we call the thermophractic force. So the thermophractic force occurs when a particle is basically moving under a temperature field, okay? So what happens is that, let's say we assume that this is a hot surface and this is a cold surface, okay? So you have air molecules that's moving around in this gap here. But what happens is that for the hot surface, the air molecules are going to have a faster velocity, okay? So they're going to carry a larger kinetic energy. So if you have a particle that's suspending in here, then the molecules on the left-hand side, which is near the cold side, is going to have a larger momentum when they collide with a particle. Well, for the particles on the right-hand side, their momentum is smaller because their speed is smaller, right? It's slower. So this is going to give this particle a net velocity that's moving from the hot to the cold. Okay, so this is the thermofractic force, and actually people use this force a lot when we are trying to preserve some art pieces. For example, if we go to the museum, let's say you can enjoy a lot of paintings on the wall, right? So for the paintings, they actually create a hot area that's behind or on the frame of the painting. Okay, so what will this do? It's gonna generate a hotter surface that will repel the particles from getting deposited onto the painting. So it's going to protect or prevent the painting from getting dirty. Okay, so this is how we can apply this force onto the particles to do something good. So there can be a lot of other forces. For example, the electromagnetic force, right? If the particle moves in a magnetic field, then because of the charge in there, the particle is going to do some spinning and so on. But if you summarize all of these forces, you can see that these forces are actively placing onto the particle. Okay, so it's also because of the field or the external field. It's because these particles are in this field that the force can act onto this particle. We can also see that these forces are active, okay? So it's being added onto the particle. But there's also a passive force, which we actually didn't realize so much about it. That is called the drag force. Okay, so the drag force happens whenever there's a relative movement between the object and the fluid that's surrounding the object. Okay, so for example, if we're trying to walk in the hallway, okay, so when you walk at the normal speed, you can feel the breeze that's passing by your face, by your ear, right? When you run, you feel that this breeze gets stronger, right? You can feel the resistance on you, and that is actually the drag force. Okay, and then you may wonder, well, is that so important? You feel that the drag force doesn't have a lot of resistance, right? Because when we walk, we don't feel a lot of resistance in there, and especially, I mean, we probably only feel that when there are tornadoes, okay, or very strong winds there. But as a matter of fact, this drag force is very important to a lot of the scenarios, especially for the particulate matter or the PM, okay? So we know that the PM is any stable cluster that's suspended in the air, right? So because of that, a raindrop is also a PM, okay? So the raindrop, when it falls from the sky to the surface of the earth, it has to endure this drag force as well. And I'm going to do a simple calculation to show you why the drag force is so important for the raindrop. Okay, so let's try to estimate what is going to be the speed or the final speed of a raindrop if there is no drag force. Okay, so if we consider the raining process, let's assume that this is our ground, and then there are some clouds that's hovering upon the earth, right? And then we know that whenever it rains, there are rain droplets in the cloud, and then they are going to settle down. Okay, and typically for these raining clouds, they have a height of around 2 kilometers. Okay, it can be higher, it can be lower, but on average, the height is around 2 kilometers. So how do we calculate the final velocity of the raindrop when it reaches to the ground? We have to do a force analysis, right? We have to analyze the dynamics of this single rain droplet. So what happens is that if you analyze the force on the particle, right, it's going to have gravity. As we said, everything on the earth has the gravity, okay? So there can be buoyancy, but if you see the equations that we just listed, so the buoyancy, if you compare the difference between these two, the major difference is just the density, right? So the gravity uses the density of water, which is 1,000 kilograms per meter cubed. But for buoyancy, it's just the density of air, which is 1 kilogram per meter cubed, right? You can see that actually the gravity is much, much larger than buoyancy. So we can just ignore this buoyancy here. So FB, we assume that this is close to 0. Okay, so if we assume that there's no drag force, then what happens is that the particle is just, or the raindrop is just going to fall freely. And we can set up the movement of the particle based on the Newton's second law. Okay, so that is ma. So a is the acceleration. Right, it's going to be equal to mg, which is all the force that's acting onto the particle. Okay, so we can cancel out m here. And further, we know that the a is basically dv dt, right? That's equal to g. And then we can try to solve what is a v. So v is just going to be equal to g multiplied by t, okay? So as the particle, or as the raindrop further falls in the sky, right? If we count the time, then the velocity of the raindrop is just the gravity multiplied by time, okay? So then the question comes, so how do we calculate the final velocity of the droplet, right? We know the distance from the cloud to the ground, that's 2 kilometers. We know the velocity as a function of time, right? So we can integrate this velocity, right, to get distance. So basically we have the integral of gt dt equal to s, and this is 1/2 gt squared. Okay, so the integral of gt is 1/2 gt squared is equal to s. And we know that the S here is basically the distance. That's going to be 2 kilometers. That's 2,000 meters. So now we can calculate what is the time for this raindrop to fall onto the ground, right? So you have GT squared equal to 4,000. And then G, let's assume that this is 10 meter per second squared, okay? So you just plug in 10, you have T squared equal to 400. And then T is equal to 20 seconds, okay? So if we assume that there's no drag force, it's gonna take around 20 seconds for the droplet, for the raindrop to fall onto the ground. And now we can calculate what is the final velocity. So the final velocity is just G multiplied by T. That's 10 multiplied by 20. That's 200 meters per second. Okay. So this is the final velocity of a raindrop if we assume that there's no drag force. So what's the meaning for this velocity? Okay, is that large? Is that small? Right? Or is that common? Because whenever we saw the raindrop outside, right, we never use like a ruler or a timer to measure the speed. Is that a reasonable number? So it turns out that for the bullets that's typically used in the guns, right? So their velocity is larger than 180 meters per second. Okay, there can be faster bullets, there can be slower bullets, but you see that if there's no drag force, it's going to be like raining bullets outside. Okay, it's going to cause a lot of damage. So as a matter of fact, there are people doing these measurements, and especially in the atmospheric science, they want to understand how fast these raindrops settle down to see what is the intensity of the precipitation. So on average, the raindrop velocity is around 10 meters per second. Okay, so you see that this 10 meters per second is much, much smaller than the speed when there's no drag force. And it actually shows that the drag force has a very, very large or very important property here, or it's of significance in our daily lives. Okay. So this is how the drag force may affect our daily lives. And I have to say that this is something that people have found very early in the history. And actually, people have started to analyze how to calculate the drag force from a very early time. It's around the time of around 1680. Okay, so it says, I have wrote here, this is Newton's form. So it's around the era of Newton, and this guy was pretty busy during that time, right? He found so many laws for the movement, right? And he also came up with this equation to predict what is the drag force. So the drag force in Newton's form is written as 1/2 rho F VR squared AP and CD. Okay, it's the basically multiplying a lot of terms together to calculate this drag force. So I can write out the meanings for each term, right? So the rho F here is the fluid density. So it's going to carry the unit of kilogram per meter cube. Let's say if it's just air, then the fluid density or the air density is around 1 kilogram per meter cubed. Okay, so the VR here is the relative velocity. So this is the relative velocity between the fluid and the particle, okay, and the object. So basically, what this means is that if the fluid and the droplet and the particle move at the same speed, then the VR is equal to 0, right? For example, if we have a wind that's blowing at a speed of 1 meter per second, and we're running at the speed of 1 meter per second in the same direction, then there's no drag force because the wind is not stopping us, right? So this is the relative velocity and has a unit of meter per second. And this AP here is the cross-section area. So it has a unit of meter squared. Okay, so the cross-section area is basically the area that's perpendicular to the fluid's motion or perpendicular to the relative velocity. So what happens is, let's say there's a particle that's dropping down to the ground, right? The raindrop, right? And we know that the relative velocity is going upwards, VR, right? So because we assume that the air is stagnant, okay? So the particle settling down, then the relative velocity is going up. So the cross-section area is just the area that's perpendicular to the relative velocity, okay? So for a sphere here, then this area is just a circle, the area of a circle. If we further assume that this is a spherical particle, right, the cross-section area would just be pi over 4 dp squared. Okay, so this is the area of a circle, right? And then CD here is what people call the drag coefficient. So this drag coefficient is unitless, okay? It doesn't have any unit. So at Newton's era, he found that this drag coefficient, we can just plug in 1 or as a constant in this drag force expression here. But later on, actually, people found that this drag coefficient should take different values depending on which condition we're at. Okay, but before we talk about that, let's first look at this equation, because we may be quite amazed by what he has done at that time. Okay, so you may wonder, well, how did he came up with these different terms and decide to multiply them together? But if you look at these different terms, they do make a lot of sense, right? For example, the rho F. So the rho F is the fluid density. Okay, let's try to imagine. Okay, so if we are trying to pull a particle in the air, right, at a speed of 1 meter per second, and if we apply this same movement in water, okay, this is air, this is water. So we know that in water, it's going to be more difficult for us to pull the particle at the same speed. And this is because of the density, because water is so dense that it prevents the relative movement of this particle here, right? So this means that the drag force should be proportional to the fluid density, okay? So the same thing for VR here. So VR is the relative velocity. So if we want to pull the particle in the air at a speed of 1 meter per second and at a speed of 10 meters per second, the drag force will be very different, okay? So I think the advantage or the achievement that Newton has done is he found that we should use the VR squared in this equation. But as a matter of fact, it's not squared. We can show that later on, okay? So everything is dependent on which CD value, which drag coefficient value we're using. And then about the AP, okay, so cross-section area. So I'm not sure if you have done the skydiving, okay? So I think maybe only a few people have tried that. It's very dangerous, at least from my view, okay? So if you do skydiving, then let's imagine which is going to give you the larger drag force. Is it stretching your arms and the legs, or is it a condition where you squeeze like a ball, okay? So the drag force is going to be larger when you stretch your arms and legs, okay? So that is affecting the cross-section area of this person, okay? This also makes sense. So the larger the cross-section area, the larger the drag force, okay? So if you look at these terms, they're not so surprising that they show up in this drag force term, okay? But I'm not trying to underestimate the achievement of Newton, what he has done in creating this equation. But I mean, from our perspectives, they're pretty much the common sense. Okay. So then let's spend some time to talk about the CD. Okay. So the CD, as we said, is called the drag coefficient. At the year of around 1680, people thought that the CD is just a constant. Well, it turns out that people found this is not a constant. And actually, the CD is a function of the Reynolds number. Okay. Well, I think probably all of you have taken the fluid mechanics. So the Reynolds number, if we write out the equation, that's VR multiplied by rho F multiplied by dP divided by mu. Okay, so here the VR again is the relative velocity, right? The rho F is the fluid density, right? And dP is the particle size or the characteristic size of this settling object. Okay, so the size. And the mu here is called the dynamic viscosity. We know that the Reynolds number is a dimensionless number. It has a unit of 1. Okay, so if you plug in everything here, you will find that the dynamic viscosity of the air has a unit of Newton second per meter squared. Okay, so and also in terms of the value for this dynamic viscosity, so for the air under standard condition, it has a value of 1.8 multiplied by 10 to the negative 5 Newton meter per square meter. Okay, so then actually we can find out why Newton decided to use one, or basically use a constant for this drag coefficient. So if you consider the objects that he dealt with in his era, normally the size of the objects are pretty large. All right, so they're probably in the scale of 1 meter. Okay, so at that time people didn't know about the particulate matter yet, right? So the rho F, we know that for the air is around 1. Okay, so the relative velocity, let's say 1 kilogram per meter cubed, and in terms of the relative velocity, so that should also be the range or the order of 1 meter per second, because that's kinds of the observable speed. So if you see all of these terms on the numerator and compare the value in the denominator, you can see that the Reynolds number is much, much larger than 1,000. Okay, we know that if the Reynolds number is much, much larger than 1,000, then we're in the turbulent regime. So in the turbulent regime, it turns out that the CD is indeed a constant. Okay, so we can show that later on from a figure. But before we talk about that, let's first try to understand this drag force better. Okay, so let's imagine that we have a wind that blows at the speed of 1 meter per second. And then we have two particles. This is particle A, this is particle B, and the wind speed is 1 meter per second. Okay, so the particle A has a speed of 1 meter per second in the same direction, while the particle B has a speed of 2 meters per second. Okay, let me write out these speeds here in the same direction. Okay, so it's asking for what is the relationship between the drag force on particle A and particle B. So we're going to calculate the ratio between the two forces, or basically the values of these two forces. So I'm going to create a pool for you guys to fill in, and then let's spend some time on this. Okay. So remember, the drag force considers the relative velocity. Okay, so it's not the absolute velocity on the particle. Okay, 5 more seconds. Okay, we'll stop here. So I have to say that this time, the correct answer is in the fewer people, okay? So it should be 0. So the reason behind that is if you look at this equation again, the drag force equation, okay? So what we're plugging in is the relative velocity between the particle and the flow, okay? So in here, we already know that wind is blowing at a speed of 1 meter per second, and the particle A has a speed of 1 meter per second in the same direction. So what is the relative velocity for A in the against the ambient velocity or the wind velocity? So the VR for A should be equal to 1 minus 1. It's 0 meter per second. Okay, and the relative velocity for particle B, that should be 2 minus 1. That's 1 meter per second. Okay, so 1 is 0 and 1 is 1. And then when you plug in the relative velocity in the drag force equation, you see that for the particle A, the drag force should be 0, right? It's just like the example we gave about, let's say we run outside at a speed of 1 meter per second while the wind is blowing at 1 meter per second. Then at that situation, we will not feel any drag on our body, right? So here I will relaunch this pool and just try to confirm that you guys understand this concept here. Let's see. Five more seconds. Okay, we'll stop here. Yeah, so it seems that this time you all understand this concept, okay? Yeah, so this is the drag force and how we can apply that. And one thing that I really want to stress is the relative or the concept of the relative velocity, okay? So this is going to be pretty important when we talk about the PM removal devices and how they're going to use this relative velocity to solve the movement of the particle in those devices. Okay, so let's get back to the drag coefficient. Okay, so the CD value. Remember here, we derived the CD, right? Or we actually show the CD is the function of the Reynolds number. And we show that in the time of Newton. Okay, so the objects or the system that he was dealing with is mainly for turbulent systems. So this is a table that's showing you how does the CD change as a function of the Reynolds number. Okay, so you can see that the CD is very large when the Reynolds number is small. And then when it gets to the larger Reynolds numbers, it's almost a constant. Okay, so for example, let's look at the spheres. So the spheres is basically this solid lines here. Okay, so you can see that for a period where the Reynolds number is between, let's say, 1,000 and 100,000, the CD is very constant. Okay, so that's why when the drag force equation first came out in the year of 1680, people assumed that the CD is a constant. But it turns out that when the Reynolds number is smaller, and especially when we're focusing on smaller particle sizes, let's say below 100 micron or even smaller, then we start to get into the scenario where the drag coefficient is not a constant anymore. And you can see that when the Reynolds number is relatively small, let's say Reynolds number below 0.1, okay, when it's in this range, this is almost a straight line, okay? So people find out that when Reynolds number is below 0.1, then we have CD is just equal to 24 divided by Reynolds number. Okay, and because we're showing everything in the log scale, right? CD value and the Reynolds number in log scale. So that's why we're going to show a straight line in this log-log plot. Okay, so what does this mean in terms of the drag force? Because we know that the Reynolds number has the value of what? Rho F VR dP, right? Divided by the viscosity, right? We also know that the the drag force has the equation like this. So can we plug in the CD and see what we find out, right? So what we can do is we'll write out the Newton's form again, 1/2 rho F multiplied by VR squared multiplied by the AP, right? And then multiplied by CD. All right, so let's start to plug in everything. So we're going to have 1/2 rho F VR squared. And then AP, as we said, for spherical particle, this AP is just the cross-section area. So that's pi over 4 dP squared. And then for the CD, that's 24 over Reynolds number, right? So that's going to be 24. And then divide by Reynolds number, that's rho F VR dP. And then the viscosity gets to the numerator. Okay, you have mu here. So we can cancel a lot of terms in here. So you see that rho F is just canceled. Okay, maybe I shouldn't cancel that term up front. It's this term here. Okay, and then the VR, one of the VR got canceled. Okay, so the same for the particle size. One of the particle size got canceled. And also you have 2 and 4, right? That's 8. And then you have 24 here. Then you've got 3. Okay, so we can write out the final answer. That is 3 pi. That is 3 pi mu dP multiplied by VR. Okay, I will box this equation here. So I want to highlight that for this class, for this air pollution control class, if there's one equation that I want you to get out of the class, okay, if I only want you to memorize one equation, it's going to be this equation. Okay, so next time or in the future classes, I'm going to give quiz questions to let you write out the equation without referring to the notes or the books. Okay, so it's the drag force is calculated by 3 pi mu dP multiplied by VR. Okay, where the mu is the viscosity, the dP is the particle size, VR is the relative velocity. Okay, so FD is equal to 3 pi mu dP multiplied by VR. Okay, so this is the most simple and I would say elegant form of the drag force. Okay, let's try to memorize this. All right, so this is what we can derive from the Newton's form of the drag force. So what happens is that as people know more about the physics or the calculus and everything, right, in the 19th century, right, people start to realize that the movement of a particle in the fluid, let's say this is a particle, and then there's fluid passing by the particle, right? They're just going to pass by and then come back. The same thing here. So the movement of a fluid that's surrounding the particle it really can be solved by the governing equation in the fluid mechanics. We know that the governing equation in fluid mechanics is called the Navier-Stokes equation. Okay, so basically for any fluid systems, we can use the Navier-Stokes equation to solve what is the force, what is the movement, or what is the the velocity of the fluid that's surrounding or in this problem here. And it happens to be that the Navier-Stokes equation, if we apply that onto the drag of the particle or onto the movement of a particle in the fluid, we can get an analytical solution. So what the analytical solution means is that we can get exactly the correct or very accurate answer based on mathematics. Okay, so it's going to be always correct. Okay, so we can derive what is happening, what is the force, what is pressure onto this sphere in here. So here I'm going to write out some equations. You don't have to memorize that, but if you're interested, you can do some calculations to confirm that the Navier-Stokes equation can be used to derive this drag force. Okay, so basically what happens is that this drag force term is called the Stokes form, right? That's derived from this Navier-Stokes equation. Okay, so from this Navier-Stokes equation, we can basically define two different types of forces. So one of the force is the force that's perpendicular to the surface of the sphere, and the other force is the force that's basically tangential or along the surface of the sphere. Okay, if you assume that this force is called P, this force is called tau, and by solving the Navier-Stokes equation, we can get the exact form of P and tau. So P is equal to P0 minus 3 pi minus 3 over 2 mu VR r cosine theta. Okay, so this cosine theta is basically the angle that's at any location relative to the central axis of this sphere, okay, or along the direction of the fluid. So this is the angle theta here, okay. So the R can be any location in the space, right, R. And this capital R here is the diameter of the sphere, okay. So we can calculate the pressure at any location in the system. And also we can calculate this tangential force, which is 3 over 2 mu VR divided by R. Okay, so again, you don't have to memorize these equations. You can just copy them down and then do some integration to find out the drag force. Okay, so this is tangential force. And with these two different forces, we can calculate what is the total force acting onto the particle. So the total force on the particle is just the integral of these two forces, P plus tau, and then along the entire surface on the sphere. Okay, so people find out that this force is basically pi over 6 rho R rho F dp cubed rho F G plus 3 pi mu dp multiplied by VR. Okay, so by integrating these two terms, by using some knowledge in the calculus, you can find out that the total force acting onto the particle can be separated into two terms. Okay, so what is the first term? So this pi over 6 dp cubed, this is volume, right? Volume multiplied by the rho F multiplied by G. This is a buoyancy. Okay, so the buoyancy is really the force that the fluid acting onto the particle. Okay, so what about the second term? 3 pi mu dp multiplied by VR. That is the drag force. Okay, so that's the drag force that's derived from the Newton's form. And we'll have to appreciate, now we have to appreciate what Newton has done in his era, because when this equation came out, it was around the year of 1890. Okay, so 200 years later, we found out that this equation, or the Newton's drag force, is indeed accurate. And I have to say that there are a lot of genius people in our history. So this is an example, and I think Einstein is also an example, right? So people even get Nobel Prize by just confirming Einstein what he predicted 100 years ago. So that's really amazing. Okay. So again, I want to highlight that you need to memorize this equation. Okay, 3 pi mu dp multiplied by VR. So this is the form of the drag force, and you see that when we try to calculate the drag force, we came with two different approaches, right? At two different times. We have the Newton's form, we have the Stokes form. Okay, but what they eventually find out is that for the Newton's form, you really have to decide what the Reynolds number is. Okay, so if the Reynolds number is above 0.1, then you have to use the equation of 1/2 rho f VR squared, let's see, AP, and then CD. But when the Reynolds number is smaller than 0.1, then the Stokes form has the same equation compared to the Newton's form. That is 3 pi mu dp multiplied by VR. Okay, so again, this is the most important equation in our class, right? So you see that, I mean, during the time of the Stokes, this is also the time when people start to realize that there are different length scales of the objects, right? We can get particles with micrometers, but what about further smaller, when we get to nanometers? So when we get to nanometers, is the equation still going to work, right? So that's when we should introduce the slip correction factor. Okay, so if you look at this system here, basically the fluid is passing by the sphere, right? We assume that the gas molecules, basically, the gas molecules of oxygen and nitrogen, they're being dragged on the surface of the sphere, right? But if we further zoom in, let's say we make the particle shrink, okay? Let it get smaller and smaller, okay? Even it gets to a point, okay? Until it has a size that's similar to the gas and oxygen molecules. So will these molecules still drag on the surface of the sphere? You know, the sphere is already very small, okay? And the gas molecules, they're not going to get in contact with the sphere at any location. So what happens is that for the particle that's much smaller, it's just going to be the collision, okay? So there's not going to be a continuous movement on the particle anymore. Instead, it's just a single collision, okay? So what we call this process is called the slip process. So basically, when the particle gets really small, it cannot have a very large drag force anymore because the gas molecules is not getting into a very good contact with the particle, okay? So we add this slip correction into the picture, and we define a parameter that's called the Cunningham slip correction factor. So what happens is that this drag force equation, really the complete form should be 3 pi mu dp divided by c multiplied by VR, okay? So the c here is going to have a larger value when the particle size becomes small, okay? So here I'm giving you some examples. For example, when the particle size is very small, it's like 10 nanometer, and the c's value is very large, right? Which means that the drag force is actually getting decreased because there's not a good contact between the particle and the gas molecules. So we're going to give you more expressions on how to calculate C in our next class. Okay, so that's it for this class, and let me know if you have any questions.